Okay, so when we have a value for the thermal expansion, which here they use the signal delta for the thermal expansion. Notice that they're not using delta L, they're not using delta D, they're using delta. So delta is in inches. So if I find out that my run of pipe is going to expand 5 inches, and the pipe's actual outside diameter is a 6-inch pipe, then I'm going to take sort of the square root of 30 there, and I'm going to multiply that by 6.225, and that's going to give me the length in feet. This is the length of leg BC required to accommodate thermal expansion in long leg AB. So the diagram is key here. If I've got 200 feet between A and B, I can calculate the delta for that 200-foot length using numbers from that table. And then I can tell you how much of an offset leg to the next support you need to allow it to flex, just as the phantom lines in the drawing show you it will flex. How much force will that cause? Well, the force that will cause in the pipe depends on the modulus of elasticity, the moment of inertia of the pipe, that is the area moment of inertia, the length of the offset leg, and the deflection. So you'll be reminded what area moment of inertia is as we go through our dynamics stuff and statics stuff and mechanics of material. So that's how you do that. Once they give you a value to use for delta, fairly straightforward to calculate L. An L bend, is there a certain force that leg formula keeps it under? Well, there certainly could be. There's going to be an allowable stress. So this creates a bending force here, and which would create a reaction force there. And you could look at that as a moment arm. So we've now got a piece of pipe here with a force like this opposed by a force like that. Force. And we're going to be bending that pipe. So you can now find the bending stresses, do a shear and bending moment diagram, and go on to analyze the wall of the pipe using that force value. Which would be too much for them to do in a single exam problem for, that'd be a 12-minute problem, so that wouldn't be within a single problem. If you don't want to do an L bend, because you're not making a 90-degree turn, well, maybe you want to make a Z bend, so your pipe can continue on roughly in the original direction. So again, we can calculate L. Notice the symmetry implied here. We've got a guide that's distance L back from the corner. We've got a middle length here of L, that's the same distance, and the same distance here again. So there's some symmetry suggested in your placement of these guides. So we only need to calculate that one value called L, and same routine. L is 4 times square root of expansion and times diameter in inches. Pay attention, L is going to come out in feet, even though everything else you plug in is in inches. So just keep that in mind. And there's the force for it. And it's in comparison to a standard value of 4,000 pounds per inch. So it's a little weird. Just plug into the formula. That's all you need to do. So here's the symmetry. Distance from guide to offset should be equal to offset length. Offsite must be supported with hangers, slides, and springs similar to those for L bends. So these are guides. These aren't anchors. So we're not rigidly attaching to it. The pipe can slide back and forth in that.